Hello and welcome to Grace Tutorial. In this video lecture, we will be discussing about one of the most important parts of the aldehydes, ketones as well as the carboxylic acids. That is all about the structure of carbonyl group. Well, initially in the previous lecture, I had already explained that the aldehydes and ketones are the organic compounds which are also referred to as the carbonyl compounds due to the presence of the carbonyl group. And the carbonyl group, which is present in both the aldehydes as well as the ketones, play a very big and the important role. And the chemistry of the aldehydes and ketones can be studied on the basis of the carbonyl group which is present in these compounds. That means the carbonyl group will determine the chemistry of these compounds. Well, if you write the carbonyl group, then you have CO. So this is the carbonyl group. So here in this carbonyl group, the carbon atom of this carbonyl group is sp2 hybridized. The first point, the carbon atom of the carbonyl group is sp2 hybridized and it is planar in structure, which is having the bond angle 120 degree. So once again I just repeat the point. The carbonyl group which is present in the aldehydes and as well as the ketones play a very important role, and the chemistry of the aldehydes as well as the ketones, it determine on the carbonyl group. That means the carbonyl group only determines the chemistry of these compounds, which the aldehydes as well as the ketones. Well, carbonyl group means CO, that is carbon and oxygen. Here we look at the carbon and oxygen. Here the carbon atom of the carbonyl group is sp2 hybridized, which is planar in structure as well as the bond angle. What is the bond angle? 120 degree is its bond angle. So this is the carbonyl group. But we need to understand that what is the structure of the carbonyl group. But before knowing the structure of the carbonyl group, let me tell you one thing. Since the carbon atom is a hybrid orbital, that means the sp2 hybrid orbital. So what about the unhybrid orbitals? The unhybrid orbitals lies perpendicular to this group and overlap. That means there will be a sidewise overlapping. That means the unhybridized orbitals lies perpendicular to the plane of the hybrid orbitals and overlap in a sidewise manner with the half-filled oxygen atom. With the half-filled oxygen atom to form pi bond. So if we draw the structure of the carbonyl group, you can understand it very clearly. Well, carbonyl group, we have C, single bond. Whoa. Here, look at here, we have C double bond O. That means the double bond exists between carbon and oxygen, right? So first of all, I have written the carbon and oxygen. Here the double bond refers to one is sigma bond, another is pi bond. We know that there are, the covalent bond is divided into two different types. That is sigma bond as well as the pi bond. So what do you mean by this sigma bond? Yes, the sigma bond is one type of the covalent bond which is formed by the head-on overlapping of the atomic orbitals. So when there is a head-to-head overlapping, that means the sigma bond is formed by the head-on overlapping of the atomic orbitals. Since the overlapping takes place in a great manner, in such a great extent, that's why the sigma bond is also referred to as the strong bond. Similarly, what is this pi bond? The pi bond is formed by the sidewise overlapping of the atomic orbitals. But the overlapping does not take place in such a great manner. That's why the pi bond, which takes place in the sidewise overlapping. That means the pi bond is formed by the sidewise overlapping of the atomic orbitals. It's very clear to understand. Covalent bonds are of various types. One is sigma bond, another is pi bond. The sigma bond is formed by the head-on overlapping of the atomic orbitals. Since the overlapping takes place in a great manner, that's why the sigma bond is also known as the strong bond. Similarly, the pi bond is formed by the sidewise overlapping of the atomic orbitals. So as comparison to the head-on overlapping, the sidewise overlapping does not take place in a great manner. That's why the pi bond is also known as the weak bond. So that's what here we are going to discuss. In the carbonyl group, we have double bond. That is, one bond is sigma bond, another bond is pi bond. But how could we understand that one bond is sigma and another bond is pi bond? In order to understand that one, we'll have to look at the structure. Just have a look at the structure. The carbonyl group is there, carbon and oxygen, right? And here in this case, between this carbon and oxygen, there is a sigma bond. A sigma bond is formed here. But the half-filled orbitals of this oxygen atom, this overlap in a sidewise manner. That means, since it is overlapped in a sidewise manner, that's why a pi bond is obtained here. In this way, a sigma bond as well as a pi bond is there between the carbon and oxygen. So this is, this is the structure. This is the structure of the carbonyl group. But if we draw like this, electron cloud, this is sigma, right? And the electron cloud will be like this. Yes, this is pi bond electron cloud. Pi bond electron cloud. This is pi bond electron cloud, and this is sigma bond. So this is what, here it is sidewise overlapping. Since these two orbitals are overlapping in a sidewise manner, that's why it is pi bond. And since here between this carbon and oxygen, the overlapping takes place, the head-on overlapping. That's why this is a sigma bond is formed. That means between the carbon and oxygen, a sigma bond is there. But the pi bond is also there, which is formed by the sidewise overlapping, which is found in this structure. Well, if you look at this one on the rearrangement or on the modification, that is a pi bond electron cloud. So here the pi bond will be, the electron cloud of the pi bond will be like this. This is basically the electron cloud of the pi bond. So we simply write, yes, one is sigma, or another we can say the pi bond. So this is what we need to understand. That is, this is the structure of the carbonyl group. But I would like to highlight a point here. If you look at here, the carbon atom of the carbonyl group is sp2 hybridized, no doubt. But here the carbon atom, since this carbonyl group is basically a polar compound. The carbonyl group is polar in nature. Now you may have a doubt that what do you mean by the polar as well as what do you mean by non-polar compounds. You see, the covalent compounds are further divided into two types. One is the non-polar covalent compounds, and number two, the polar covalent compounds. So what do you mean by the non-polar covalent compounds? You see, when the shared electron pairs, suppose I have the two atoms, that is A and B. Let us imagine that I have two atoms, that is A and B. If the shared electron pairs, that is which is connected between A and B, if these shared electron pairs are equally distributed between these two atoms, then that then that compound is said to be a non-polar covalent compound. So in the case of the non-polar covalent compound, the electronegativity difference is not there. That means the electronegativity difference is 0. That means the covalent compound is said to be non-polar. A compound is said to be non-polar covalent compound if the shared electron pairs are equally distributed, so that the charge separation does not take place. That means there is no charge separation. There is no separation of the charge. The molecule is symmetrical and which is electrically neutral. So what are the examples of the non-polar covalent compounds, right? You know the examples like hydrogen, chlorine, nitrogen. So these are the various examples of the non-polar covalent compounds. That means in these examples, since these atoms are identical together, there is no electronegativity difference. As a result, the shared electron pairs are equally distributed between these two atoms. So there won't be a charge separation. This non-polar covalent compound, now you may have a doubt, can the non-polar covalent compound be formed in between the two dissimilar atoms? Yes, the non-polar covalent compound can also be formed between two dissimilar atoms due to a slight electronegativity difference. Well, I have methane, CH4, right? If you look at the methane, we have the electronegativity difference of the electronegativity of the carbon is 2.5 and hydrogen is 2.1. And since there is a slight electronegativity difference between the carbon and hydrogen in case of the methane molecule, right? This compound is also said to be as a non-polar covalent compound. That means the non-polar covalent compound, we can say that in the identical atoms, as well as it exists in the identical atoms, as well as it also exists in the dissimilar atoms, that means non-identical atoms. That means these compounds do not ionize in water. This is one of the most important points that we need to remember. Okay, that's all about non-polar covalent compounds. But what is all about the polar covalent compounds? You see, a compound is said to be polar if there is an electronegativity difference between the two. Suppose you see, I have HF, hydrogen fluoride, right? I have a hydrogen fluoride. What is the electronegativity of this hydrogen? 2.1 and fluorine is 4. Since it is having the high electronegativity difference, right, the shared pair of the electrons will be attracted more towards the electronegativity. It will be attracted more towards that atom which is having the highest electronegativity. So we need to understand that what is the definition of electronegativity. Electronegativity means nothing but the tendency to attract the electron towards itself. So due to the high electronegativity of the fluorine atom, the shared electron pairs will be attracted more by the fluorine atom than that of the hydrogen atom. As a result, there is a charge separation takes place. That means the hydrogen atom, it occupy a slight positive charge. On the other hand, the fluorine atom will occupy a slight negative charge. So this is what here also it takes place in the way. That is, if the carbonyl group, here in the carbonyl group, in carbon, a slight positive charge is created. Since the oxygen is highly electronegative in nature, a slight negative charge is obtained. And these compounds can ionize in the water as well. And we also can give the various examples of the polar molecule, right? I can show you the various examples of the polar molecule. Suppose you see water. Water is also a polar molecule, and there are other polar molecules such as you see ammonia. Nitrogen also shows the polar molecules. That means there are various other such molecules, water molecule, ammonia molecule, right? And the carbonyl molecule, all of these are polar in nature. So since they are polar in nature, a slight positive charge is created here in the carbon atom and a slight negative charge is created here in the oxygen atom. I hope it is very clear to you that this carbonyl group is polar in nature, right? That is the point we need to understand from here. So I hope you understood the structure of the carbonyl group. And here next we will discuss about the difference or the similarities between the carbonyl group as well as the ethylenic double bond. Well, if we look at the similarities as well as the dissimilarities of the ethylenic double bond, ethylenic double bond and carbonyl group. First of all, let us have a look at the similarities. Well, the ethylenic double bond and the carbonyl group, the first point is that both consist of double bond. Both consist of the double bond, right? So here in this double bond, one bond is sigma, one is sigma and another is pi bond. So what are the similarities? Yes, the first one similarities is that, you know, in the ethylenic double bond as well as in the carbonyl group, it consists of double bond. Though it may be the ethylenic double bond or carbonyl group, it consists of double bond. And in the double bond, one bond is sigma and another bond is pi bond. And both are planar in structure and having the bond angle nearly 120 degree. And both shows the addition reactions. Both the compounds such as the ethylenic double bond and the carbonyl group shows the addition reactions. They have the bond angle 120 degree. Well, so what are the dissimilarities? The dissimilarities is that the carbonyl group is basically polar, which we had discussed right now. I hope you understood that what do you mean by polar as well as the non-polar. The carbonyl group is polar. On the other hand, the ethylenic double bond, the carbonyl group is polar, but ethylenic double bond is non-polar. In case of the ethylenic double bond, no charge separation takes place, but in polar, the charge separation takes place. Here the slight positive or the negative charge is created in case of this polar, but this is non-polar. That means, what is the dissimilarity between ethylenic double bond and carbonyl group? Carbonyl group is polar. On the other hand, the ethylenic double bond is non-polar. First point. Second point is that, and in the similarity I had said, both the compounds, that means both ethylenic double bond as well as the carbonyl group, show the addition reactions. But here we need to look at the carbonyl group shows the nucleophilic addition reactions. Carbonyl group shows the nucleophilic addition reactions. On the other hand, ethylenic double bond shows electrophilic addition reactions. Electrophilic addition reactions. So once again, the dissimilarities. The dissimilarities is very simple. You need to remember these 2 points. Ethylenic double bond is non-polar in nature. On the other hand, the carbonyl group is polar. Similarly, carbonyl group shows the nucleophilic addition reactions. On the other hand, the ethylenic double bond shows the electrophilic addition reactions. Well, this is the dissimilarities as well as the dissimilarities of the ethylenic double bond as well as the carbonyl group. And what I have drawn here in the beginning, this is all about, some of the examples of, this is formaldehyde, this is acetaldehyde, and this is acetone. I've written here the bond angle, right? The bond angle between this oxygen and, hydrogen in case of this formaldehyde, and oxygen and hydrogen in case of acetaldehyde, oxygen and hydrogen in, oxygen and methyl group in case of, this acetone. I think it is a little bit helpful for you. Well, I hope you understood the structure of the carbonyl group. I have drawn the structure for you and made you very much clear. Along with at last we discussed both the similarities as well as the dissimilarities of the ethylenic double bond as well as the carbonyl group to make you very much clear. So this is all about today's session, and due to the lack of time I'm not able to go ahead, and tomorrow that we are going to discuss one of the most other important parts of this chapter, that will discuss much more about the general methods of the preparation of the aldehydes as well as the ketones. Anyhow, thanks for watching for today, and if you'd like to watch the next part, I request you to press the bell icon over here to get the latest notification. Thank you very much for watching.